Hi, good evening. My name is Sunim Nazar. I'm from the data platform team at Dream11. This is our second session today from Dream11. Earlier in the day, my colleague Bipul has presented about the optimization we made on our consumer side. The optimizations we made in order to cater to our throughput requirements at Dream11 without any other potential risk of data loss or latency. First of all, thanks to you all for taking part in this session. This is the last session of the day. Most of us are tired already, but I'll try to keep it easy and quick. Just a quick question. Has anybody thought about RackAware Partitioner on the Kafka producer side before? Has anyone implemented one such at your organization, or has it had a similar thought in your mind? So let me start with a few words about Dream11. Dream11 is the world's largest fantasy sports platform. Here, the users can create virtual teams of players that play a real match and compete with other users or friends based on the performance of this virtual team in the real match. As we speak, we have over 230 million registered users. We cover 12 sports, and the peak concurrency we have handled so far is 15 million. This was in the last IPL. We are very big users of Kafka. We have a lot of big Kafkas, and everything is self-hosted currently. We face a day-to-day ingestion of 44 terabytes of data. So that speaks how important, how critical the performance of every system associated with Kafka is for us. Also, all these numbers that you see on the screen, we are hoping to break it in IPL 2025, which is starting in 3 days. So there are many use cases where it's acceptable for the business logic that the messages that you produce, it can be appended to any partition in the topic. What I mean is, OK, sure, there's a key by partitioning with Kafka topic partitions. However, there are many use cases where the throughput really matters, and you don't really care about messages of a certain key going to the same partitions. A typical example would be any event collection or log collection system that we create using Kafka. Their partitioning by key is not really important. Now, if we take a typical setup of Kafka in an organization would be hosting their system in a given cloud service provider. They would be using a specific region. Now, in order to ensure high availability, the system would be spread across multiple availability zones, or rack. In case of Kafka, the brokers that are involved, the topic and its partition that are spread across the brokers, every client, producers, and consumers, all these would be spread across different availability zones. This ensures high availability. The more diverse rack or availability zones you use, the better. However, when you have your systems spread across multiple availability zones, you're basically introducing a potential chance of cross-AZ network. And with most of the cloud service providers, cross-AZ networks are costlier compared to same AZ networks. And this became a problem for us, too. We noticed that since the traffic involved with our Kafka is over 44 TB a day, the cost associated with cross-AZ is also very significant. Just to give you a number, if we have to take compute, memory utilization, and networking on the side of Kafka producers, the networking constitutes to over 30 to 40% of the overall cost. And out of this 40%, it is, with most cloud service providers, same AZ network is almost free. It's very negligible. And it's the cross-AZ network that is charged. So that's where this 40% is coming up. And we were quite unhappy about this cost. So in order to explain this problem, I'll introduce you to one of our key services, which is called Data Highway. This is an event collection framework that we have in-house. It's built for scale. It is built for collecting events from various sources, such as user behavior events from the mobile app that we have events that are sent by third-party vendors, events that are generated by the internal systems. Okay, so at its core, it has a HTTP application which basically collects the events from different external clients, does some validations and processing, and pushes to Kafka. This is at a high level. This is what this application does. Now, Data Highway is built for extreme scale. It's capable of collecting over 1 billion events per minute. So far in our production system, we have, in the last IPL, we have collected 400 million events per minute. 400 million events constitutes to 10 GB per second. This was supported by a fleet of 250 instances on the application side, a Kafka cluster of 50 brokers. The main target topic had 200 partitions, and the whole system, the applications and the Kafkas, was spread across 4 availability zones. Now I'll just give you a brief about what is a partitioner in a producer. So when you have a producer client that receives messages to be produced to your topic partitions, a partitioner is the logic that determines what is the partitioner I should be sending this message to. Now, there are different kind of partitioners. I've just listed the main ones. The key-based partitioner is where the producer gets a message to be produced. It determines what is the key, and then sends it to the appropriate partition, making sure that messages of the same key always resides in the same partition. Round-robin partitioner is where the producer keeps on rotating between all the available partitions. So for each messages, making sure that every partition is evenly loaded. This ensures uniform distribution of load. Now, uniform sticky partitioner is an improvement on round-robin partitioner. So instead of switching the partitions at every messages, it has a configurable batch size or a linger MS, and when the batch becomes full or when the time period exhausts, that's when it switches the partition. This is extremely useful for high throughput scenario because it almost ensures even distribution of load, but doesn't have the overhead of context switching at every message. So in our data highways use case, since partitioning based on key is not very important and throughput is very, very critical, uniform sticky partitioner is what we went to. By the way, you can also implement your own custom partitioning logic. Kafka producer does give you that space. Also, in the recent releases, in the recently released Kafka versions, they have merged all these partitioners into the built-in default partitioner, where you can play around with some configuration and it serves the functionality. Now, let's take a look at the network between our application that has the producer and the Kafka broker itself. Now, in a distributed system, all the applications are spread across multiple machines, and the Kafka brokers are basically running in multiple machines, which means these machines are, again, distributed into multiple racks. So you have your application instances in different racks, and you have your Kafka brokers in different racks. In this diagram, there are 8 application instances and 8 brokers. Let's assume each broker is having 1 partition. So in this case, you have 1 producer client in one of the instances, and it has got 8 target partitions. So this means that 1 client would be making connection to each of these partitions and then producing to each of these partitions in a round-robin fashion every time a batch gets full. Now here you can see, since there are 4 racks involved, 25% of the time the communication is between 2 machines in the same rack, while 75% of the time it's between 2 machines in different racks. Okay, just one more thing to add on. When you look at from the latency point of view, typical latency between 2 machines in the same rack is mostly sub-millisecond, whereas when it's 2 machines in different rack or different AZ, it can range from 1 to 3 milliseconds. So there is a small difference there. So in this setup, we can see 75% of the traffic is constituting to a huge cost, and the average latency also goes up because of this. So when you have all your communication, this is how it looks like. Every producer client will be communicating with every broker all the time. So in our case, we noticed that the overall cost of running our application, 40% of it was contributed by the cross-AZ network. Now that's sorry, 20% of the overall cost was contributed by cross-AZ network. And if we take the if we take only the producer, that number is 40%. Now, this was upsetting for us because we knew that in case of consumer, the industry has solved it using something called follower fetching, where the consumer client, instead of reading from the leader, who may be residing in a different rack, they would read from a replica that resides in the same rack, thereby taking advantage of the same AZ cost and latency. So we started thinking, OK, we should be able to do something similar on the producer side. However, follower fetching wouldn't help on the producer side because it's not possible to do the writing into the replicas. So what's the solution? So the idea was to instruct the producers to preferably write only to those partitions whose leaders are residing in the same brokers. So if you see here, let's take the node 1, application node 1. Instead of writing to all the partitions in all the brokers, it is selectively choosing those partitions which are staying in the same rack. Now, by this, every traffic is restricted to its own rack, and there is no cross-AZ network between the client and the brokers. We implemented this with a small tweak in the built-in partitioner that Apache Kafka provides. So in order to do this, we need some information pre-hand. The client, the producer client that is trying to write, it should first of all know, OK, which rack am I staying in, and then which rack are each partition staying in, each target partition staying in. So this information has to be configured in your Kafka brokers as well as your producer, the application having your producer. Now, when we have this information, what we can do is, first of all, the client gets to know about the rack of itself and the target partitions. It can preferentially route the traffic to the target partitions that's residing in its own rack. And in case of a failure, I mean, as a fallback, let's say, for some reason, it cannot find any partition in its own rack. At that time, it would fall back to the default behavior, which is write to every partition that's available. There's not a lot of code. It's very minimal. So as you can see, this is the built-in partitioner class provided by the Apache Kafka producer. Over here, we have added one more attribute called producer rack. This is to be taken as an input from the configuration file. So it's taken as a parameter in our constructor. And then we have implemented a function. So this function basically takes all the available partitions as an input, and then it executes a filter here, which would basically keep only those partitions which are where the rack is matching with the rack of the client. And it would return that. And in case if the filtered partition is empty, in that case, it would return the original partition list. Now, the only difference is this is the method where the partitioner decides what is the partition the producer should write to, what is the next partition it should write to. So over there, where it passes the available partitions for the topic, we have applied this filter. Now, with this implemented into our system, we literally eliminated the cross-AZ network entirely. So this is basically saving us about 40% of the cost on the producer side, because now the only associated cost is the hardware utilization. And also, the average latency also comes down to sub-millisecond, just on the producer side. On the application side altogether, we had a cost benefit of 20%. Things comes with trade-offs. So in this case, the first thing is that since the load that is put on a partition is directly proportional to the number of clients that writes to this partition, here, if you remember the diagram that we have seen, a partition is loaded by the number of clients that it has in the same rack. So unless you distribute your producer clients evenly across the rack, there is a possibility that a given partitioner would be getting more load compared to a different partitioner in a different rack. This shouldn't be a problem most of the times because everybody follows a pattern of even distribution of everything across the rack all the time. If you have any reason not to do that, you should very well know, you probably know how to tune your partitions as well. So this is most probably not a concern. The second problem is at the time of very low volume traffic, at a low traffic time, you may not have enough application instances to spread across the rack. At the time, there could be a skew in your application instances, hence the producer clients across the rack. At that time, a few partitions can be overloaded compared to others. But since it's a low volume scenario, this shouldn't give a problem. Even this skew should be fine to live with. Rack-aware networking is something that's applicable to any distributed system that has a multi-AZ presence. It's not just to Kafka. So this idea can be implemented everywhere, anywhere, where there's a client-to-server communication in a distributed fashion, where the client and server can have multi-AZ presence. So this will help us improve latency. This will help us save cost. At the time when we identified the problem with cross-AZ cost, we sort of found the solution to, we were hoping that, OK, somebody in the world should have already solved this because it didn't sound very complex to us. However, our research didn't find anything to copy from. So then that resulted in us building it ourselves. However, so this was implemented at Dream11 over a year ago. However, when I was preparing these deck, I found that 2 months back, a gentleman named Ivan Yurchenko from Finland, he has created a Kafka improvement proposal on the same topic. So I collaborated with him. We'd be contributing to the open source soon so that all of us can make use of this logic right out of the Apache Kafka. It's currently paused because of the Kafka version 4 release, but soon we'll be starting with the work. That's it. As I promised, it's easy and quick, I believe. Any questions?
Yeah, you said you reduced the AZ cross DC network cost, right?
OK.
But to achieve the ISR on replica, anyway, the data has to transfer from one AZ to another, right? Within the brokers.
Correct. So the question was, anyways, there is a network happening between the leader and the replica that resides in a different rack. Now, that's a question. That's something that we cannot solve because the whole point of bringing in replicas is so that even if there is a AZ failure, we don't lose the data. However, that network happens within Kafka, within the Kafka brokers. It's independent from the clients or the producers. So here, our focus was more on saving on the network part between the client and the Kafka brokers itself.
But the amount of data transfer from producer to client and broker to broker should be same, right?
Not necessarily. Let's consider a situation where you have a replica of 2. You have one leader and 2 replicas. So one data transfer that happens between, so there is one transfer that happens between the client and the leader. And then there are 2 that is happening between your leader to replica 1, leader to replica 2. So here, basically, you're cutting down 1/3 of the overall. So it's not negligible.
Yeah, OK, got it.
Hello. Yeah, I think this solution works because, as you said, your producers are not, they can publish to any partition, right? That is why if a message comes to a producer, it can publish to the same rack partition, right?
Could you repeat, please?
In this solution, if the requirement is that I have to publish a key to a particular partition only,
OK.
Right? So then I think this won't work because that partition leader might not be in the same rack.
Correct, yes.
Right, so it's a very specific use case. That is when we are partition agnostic.
Technically, you can solve it. So instead of having one partition per key, if we build a system where you have multiple partition for the same key in different rack, this can be solved. But again, it would help only if your throughput per key is also pretty high. Typically, whenever there is partition by key, we do not see the throughput being so high. Usually, we require this key by partition in transactional systems. In a system, I mean, as you said, it's right. Only if your partition stays in the same rack, that would be possible to write. If you cannot find a partition within the same rack, then you have to fall back to crossing the rack.
Right. So use case was for maybe, as you mentioned, maybe log processing. Like, what was the use case in your case? Like log processing?
Yeah, that's where we are currently using. But anywhere that we do not partition based on a key, this is being used. I mean, this can be used.
Able to hear it? Yeah, like I used to use this Dream11 apps. Sometimes I used to see that whenever joining that contest, the connection lost, right? So due to this huge number of users joins that contest, how it will be recovered? Like,
I believe the question is about the experience that you're having on the app, is it?
Yeah.
This is out of scope for this discussion.
Like,
maybe we can take it offline after the session.
Yeah. Okay. No, I want to understand like that it is related to some Kafka or something.
That depends. I mean, the kind of interaction that you're making with the app, it tries to communicate with some service. Most probably, it's not a Kafka. Your mobile device wouldn't be able to communicate with our Kafkas directly, so it should be something else.
Okay.